Hi, I'm Michael Yosley, and today we're going to be doing a 2D simulation of a CD nozzle in Fluent, and this is for high-speed aerodynamics. Okay, we're going to start by opening the Workbench, and then we're going to drag our Fluid Flow Fluent into the workspace area. Click on Geometry. We're going to change the analysis type to 2D, because as I said, we're doing a 2D nozzle. We're going to right click on this. I prefer using the Design Modeler geometry, so we'll give that a second to open up. Okay, now that that's open, I'm turn this like this. Make sure that your units are in meters. And then we're going to go to Concept 3D Curve. And now I've already made the coordinates file for this, so just to show you what the format is for that, you want it to look like this. You have your plane, your points, X coordinates, Y coordinates, Z coordinates, and for this one, since it's all 2D, those will all be 0. And you'll want to split it up in between the top and the bottom of your nozzle, and I'll show you why in a second here. Since we're doing it from curves, open this up, and I moved mine into this area already, so we'll import the bottom one first. Zoom in on, we'll get generate first. Click generate, and we'll zoom in on it. Now there's the bottom of our CD nozzle. We'll do this again. And this is why you have to do it in two separate sections, otherwise it tries to connect all these points, and you'll end up with kind of a rounded shape on the end, which is not what you want for your inlet and outlet. So we'll go over here. We did bottom last time, we'll do top. Generate. And then concept lines from points. Where is our point over here? Okay, let's try doing the other side first. You'll have to drag it down. Have some issues with this. Click and drag. Alright, there we go. Generate that. And we'll zoom out a little bit for this other side. Kind of lighter in that corner, it's tough to see. Concept, line from points again. See if we can find this one first. Click and drag. Okay. Alright, now we have the entire shape. Line body. Concepts. Surface from edges. Now you'll click and drag on these as well to make sure that you select all of these. Apply. Generate. Now you have your surface created. Go in here, we'll make sure that that surface, you'll have to change this to fluid. Fluid. Generate again. And then right here you'll suppress this body because it will come up with issues when you go to make your mesh next. Generate, everything should be good for that. So we'll go back here, geometry has been updated, but we'll make sure it's updated with those last changes just to be sure. Okay, and then we'll double click this, we'll open up our mesh. Okay, now that we have our mesh pulled up, I go into mesh, the element size, we're going to change this to 0.01. We're going to go to sizing, change that to adaptive, click generate. And for this one, since we're dealing with an inviscid flow, we don't have to worry about doing boundary layer inflation, so we have better measurements on there because it won't make a difference with the ANSYS flow mesh. Okay, and see, this is why we deleted the line body, because that'll show up in here with X next to it, and you won't be able to move on if that's not corrected. So we need to add our name selection, so we click on that, create name selection, selection name inlet. Okay. Name selection inlet. Okay. Click on this. You'll have to go up here and make sure that you're selected on edge. Otherwise it might try to select the whole service body, and that's not what we want. Outlet. We click on these, make sure that we've selected the right things. Click generate. Now our mesh should be good. If you want more details, you can change the element size. For what we're doing, this should be good enough, and it'll slow down the computer the more elements you have in there, or the smaller your element size. Go back here to mesh, we'll right click, update. Alright, I'll double click on this and it'll take a second to pull up the setup. Alright, this will pop up before we get all the way into the solver. Select double precision, start, and it'll take another second to load up. Alright, now we've got the setup pulled up. So first we'll go to physics, operating conditions. Change this to 0. Then we'll go over here. We gotta make sure we turn the energy equation on. And we'll click on this one that says viscous SST K omega. Double click on that. Now we'll pull up this window. As I said before, we're doing ANSYS flow. Select that, click OK. Okay, that's everything that we have to do in models. So go to materials, fluid. First you have to make sure that this is set to air, which should be the default, but you want to verify anyways. You double click on that. Alright, for this one, since we're doing a high-speed flow, we need to change that to ideal gas because the density will change throughout. Change, create. And we need to change it to ideal gas because we're hitting Mach 1 or above. Fluid flow, materials. Now we'll go to our boundary conditions, inlet. This will be set to velocity by default. So you right-click on that, change it, the type. We'll change this to pressure inlet. Once you change it, this window will pop up. And for this, you'll have to do the calculations based on the isentropic tables and the information you were given. So I've already done the calculations for the information we were given. Here's our stagnation pressure, stagnation temperature. Here's the pressure at the outlet. And so this is the information that we'll need right now. That 9931877. And that will go in here. 9931877. And our total gauge pressure will be the 101,325. So we'll set that. Alright, we've got our atmospheric temperature, or pressure, P stagnation up here. So we'll click apply. Oh, we need to change our temperature as well. Our temperature is 298.299. Apply that, close it. Then we go to outlet. The default on that is a pressure outlet, so we can just double click on it. Alright, now this pops up. Our gauge pressure, we'll need to go back to our table that we made. 3728.76. Everything else will remain the same. Go to our temperature. So our temperature at the exit, 116.82. Apply that. Now everything in here be done for our setup. Setup complete. Double click on this. Now you go to standard initialization. Compute from inlet. And you can see that's popping up with the velocity at our inlet. And that's pretty close to what we calculated when we used the isentropic tables. All that. Initialize. See, the temperature is a little bit lower here too, but very close to what we had. Double click on run calculation. We're going to do 500 iterations. You can do more iterations. As soon as your residual level is hit, it'll stop. But 500 is enough to get us very close to our answer and not overload the computer. So we use 500 iterations. Between 500 and 1,000 is usually a pretty good number. Alright, our calculations are complete. I'll run through our scaled residuals while it's doing all those calculations, but I'm going to go to graphics. Want a contour, we'll do this one for static pressure. Want to select filled on here, interior surface body. Sometimes it will just say surface body, and that one's the better one to choose because that's the fluid inside. But this will give us the same results. Save and display. And you can also use this to do your velocity, your density, your temperature, everything else that you need to do here. Save and display. Close. There's our contour for our static pressure. Then we'll also go down here, we'll do a plot of the velocity just to make sure that it's lining up with the calculations that we did. We'll change this to velocity center. and we'll create a new surface, line rake, y equals 0, line, and we know our measurements will go from negative 0.5 meters to 0.5 meters. Create, close, go right along here. Select velocity, leave everything else the same. Curves. Center, apply, close, save and plot. Now since it increases the whole time, we can tell that we're hitting Mach 1 right at the throat region at x equals 0, the middle of our CD nozzle. And we'll compare this with our calculations for our velocity. We had 58.4 meters per second at the inlet, 316.9 at the throat, and 606.6 at the outlet. So let's see how that compares here. We had 58, around 300, around 600 meters per second. So it looks like everything's adding up to what we calculated before. So now we have that. We'll minimize that. You can also pull it up using the solutions. Sorry about that. It's actually the results section that you can click on. Here you can do more contours, velocity, contour, domains, locations. One. See, that's a little better because you don't have the mesh throughout the whole thing. The numbers we're getting are the same thing. And so that concludes part 1 of project 1 for high-speed aerodynamics.